Hello, everyone. Thanks for joining us for today's webinar on Arachnus networking products. I'm Ricky Pishoff, and I'm one of the technical trainers at SnapAV, and I'll be your moderator for today's webinar. Before we get started, let's go through a few quick housekeeping items. First, we will be recording this presentation, and we will send you a link via email to the video within the next few days. And lastly, we are planning to have time at the end of the presentation for a Q&A session. So please feel free to send in your questions at any time during the webinar. You can do that using the question and answer feature in the webinar control panel. Okay, now I'd like to introduce today's presenter, Aham Araksusi, who is the Director of Product Development for all of Arachnus networking products for SnapAV. Welcome, Aham, and I will pass it over to you.
Thanks, Ricky. Welcome, everyone. Thanks for joining us on this afternoon. So today's topic is going to be a very basic networking 101 kind of topic. Over the past year, as I would say, we've been communicating a lot of topics that is based on the feedback of dealers. But we see at the end of the each webinar, there's a trend of the need of having basic terminologies and basic network design, kind of understanding all the jargon and all the different elements that goes into the networking world. So this is our first attempt to do that. I'll try to simplify things during the course. There will be a lot of kind of threads that you can pull on after this. So think about this as kind of introductory way of thinking about networking. So what we will cover today is going to be basic network terminologies. We will do kind of a basic network design, very, very small network. So walk you through how to think about those components. And then, where you take things from there, from your knowledge perspective. So this will be kind of like a starting point, or one of the starting points, hopefully, on your journey to deepen your networking knowledge and get to that next level of knowledge and expertise. And then we'll have, I'm planning on having, a big time of Q&A so we can answer all the different questions that you have. All right, so let's start with, networking 101. Basically, why do we network? Why should you care about networking? And get to some jargon items and then with something that you call OSI Reference Model. So you probably see this in your daily life as a residential professional installer, that a lot of devices and a lot of solutions, they are coming out of the gate that are network-based, either Wi-Fi or wired, whether it's professional installation or DIY solutions, such as Nest thermostat, for example. So you see, a lot of solutions are network-based, and you've been asked or pulled into this world of networking because all those solutions are reliant on the network, and the end consumer, when you put a solution together, they expect you to own that solution and provide a seamless experience for them. So that's what we call that from your perspective, or from a dealer perspective, from the industry perspective, more devices that are going into the smart home, and the network is essentially the digital backbone for the current smart home and the future homes, because that technology will continue to penetrate throughout the U.S. households. But that was not the genesis of networking technology to begin with. The technology itself has been around for, I would say, 25 plus years. Started in the late 80s, and you can date it actually before then, but it started to become more mainstream in the late 80s as the dot-com boom started to come up with the internet. So really the genesis of networking as a space or as a technology or practice is centered around sharing, and that's mainly started with sharing resources. Back in the late 80s, there's a lot of, there were mainframes and computers that they need to access those mainframes, and you need to have a lot of computers to be physically attached to a mainframe, so that becomes very challenging from a scalability perspective. So they develop technologies around how can we share more resources, how can we share those servers in a corporate environment, and then that morphed into, you know, how can we share printers on the network, and how can we share files between computers one-on-one. So it's, you know, all about sharing resources, and I think that the genesis still applies today. From a technology perspective. So you think about, you know, the streaming devices. This is really sharing content across multiple devices. So you would have either a Plex server on your network that holds a movie, everyone can stream that movie, or that movie is hosted on a service provider such as Netflix, and now millions of people can access that content. But the network itself as technology, I think the best way to simplify it, or approach it from a technology perspective, I say, you know, the network system is similar to the mail system. So you can see the mail system here is like an example of a typical distribution center. You get plenty of boxes and packages and envelopes and, you know, small packages and large packages. They're going to multiple destinations, coming from either one source or multiple sources, going to one source or one destination or multiple destinations. So it's really, you know, a system, the mail system, being, you know, as old as it is designed to share those messages across multiple people at scale. So you can think about networking as an infrastructure or a framework to share content or messages digitally across multiple people. So similar to a mail system, you know, you get your message, you package it, and you put, you know, your address as your source and the destination as being the recipient address as the destination, and you just simply hand it off to a mail system or a mail provider, mail carrier. And that's, you know, the way that consumers interact mainly with the mail system. The other way they interact with it is that they receive that spam mail or junk mail on their mailboxes every week or so. So that's another way they interact with it. And they can ship, you know, personal messages. They can ship large packages. They can, you know, if they have multiple, you know, a large shipment, they can break it up into smaller shipments and ship it out. But that's what the users see. What they don't see is all the infrastructure that goes in the back end to allow this package to go from their house to the destination house. So thinking about those messages, it really gets us to the first terminology, which is types of traffic of the network. So you have, you know, one-to-one, which is, you know, I'm sending a package from me as a sender to a single recipient as a receiver, and we call it unicast traffic. So in the network technology, when I'm streaming or I'm sending a message, I'm, you know, moving a file from my computer, for example, to Ricky's computer, that's a unicast traffic going, you know, one-to-one. There's another type of traffic, which is, you know, I'm sending my message to everyone that can receive it. So I'm just, you know, spamming everyone, and you can see that as spam mail in your mailboxes. There's a third one, which is selective, kind of a group message, which is multicast. So basically, there's one sender that goes to a selective number of recipients, but it's a group recipients, not a you know, single recipient. So that's, you know, the first kind of jargon that you run into is types of traffic on the network and how it ties up to a mail system. Now, going back to the mail system, if you want to ship something internationally, the infrastructure gets even more complicated. So you can just assume that you want to have, you know, going from your house here to, you know, a recipient, let's say in the UK. So your package goes from your house to your local distribution mail center that gets on a truck to the local kind of concentration center or warehouse that goes to a port or a airport that gets freighted across the ocean to the UK and some destination port in the UK, then gets on a truck to a distribution center, then gets on a truck, a smaller truck, to a mail center, then gets distributed on a truck to the recipients. So for the sender and the receiver, they were not aware of all this infrastructure that went into play and to get that package from source to destination. So each kind of point in the infrastructure, they have different systems to track that package. They probably will not carry the small package as it is across the ocean. They most likely, box it up into a bigger box going to the UK, and then they put it all in a big pallet that goes throughout the UK that has multiple, packages and other products. So that kind of sort of communication is not going to be seamless across the board in terms of the package size or the addresses or the infrastructure to support such process. So similar thing, if you think about it from a mailing system, it's the same kind of idea in the network, but done in a digital manner. So you can think about the package, which is your data, is being packaged again as it goes down the system to get to the network, and then as you get it, from a recipient perspective, they unpackage everything to get to your content, which is the package content. So that gets us to a really important topic or framework that was developed by the IEEE, just to have, to frame the evolution and the innovation around the technology, is what they call the OSI reference model. So they broke down the flow of traffic into multiple layers that represent this packaging and what we call the encapsulation process. And those layers are, there are 7 layers. From a networking perspective, everything that is layer 5 and 7, we call it application, which is kind of the content. So we don't pay too much attention to it. But there's a layer called layer 4, which is transport. Layer 3 is called network. Layer 2 is called data link. Layer 1 is the physical one. And I will, go through each layer and give you some, examples in real life, what you should expect, and where do you see it, how do you interact with each layer. So the examples for each layer, starting from the bottom up, layer 1 is the cable. So all the cables, all the physical interfaces, you can see them in your RJ45, your Cat5 cables, your Cat6 cables, your fiber connectors, whether it's LC or SC, whether it's single mode fiber or multi-mode fiber. So all those technologies and all those standards, they revolve around layer 1, which is basically how can we carry this electrical signal or optical signal from one source to a destination. So this is the way that you see that in real life. That's everything that you touch and feel in the network world is basically layer 1. But also from a wireless perspective, all the airwaves is layer 1 technology. So picking up 2.4 gigahertz in Wi-Fi or 5 gigahertz in Wi-Fi, that is also a layer 1 kind of space that the networking world deals with. And there will be a lot of innovation and a lot of techniques that are being developed to increase the speed or efficiency or reliability of that layer 1 technology. So one example would be in the wired world is this movement, from Cat3 cables in telephones to Cat5 to Cat5e to Cat6 to Cat6a, and now we have Cat7 and Cat8, and all those movements in cables being shielded versus unshielded, and having foil and not having foil. All these innovations, they address specific needs in the marketplace. And that also enabled the physical interfaces to go from fast Ethernet to gigabit Ethernet to 10 gigabit Ethernet. So that is layer 1. It's really the physical stuff. Layer 2, this is when we get into something that is more logical, but is tied to a physical interface. So think about the layer 2 as a bonding between the logical and the physical, and it's preparation of your package to be held into the electrical wiring or the airwaves. So the way you see it in the field most commonly is what is called a MAC address, which is Media Access Control Address. The MAC address is a kind of a hexadecimal address. It is unique to each physical interface. So each network RJ45 interface, that you see on each device, whether it's a laptop or an Apple TV or a switch or whatever it is, whenever there is a physical interface, there's a MAC address associated with that physical interface. And that MAC address is a large number, it's a hexadecimal number, but it's designed to be unique for each interface. And the way it's designed, you split that MAC address in half. The first half is going to be an organizational unique identifier, which is OUI. This is basically companies like Arachnus or like SnapAV or like Apple. They go into a standardization entity and they purchase a block of MAC addresses, or they purchase a unique OUI for them, or there could be multiple ones that they purchase. But basically, the first half is a unique number that is not shared across any other company that those organizations purchase, and this basically defines their products. Now, the second half is more private, is more up to the discretion of that company or that OUI that gives them control over how many devices that they can produce or how many network interfaces they can have assigned to that block. So you can see that number is not infinite. It is large because it's hexadecimal. So it's, we got 6 to the power of 16 permutations. And that's why, multiple companies, large companies, they will have multiple OUIs for multiple products. But this is how you can see it in real life. You can see it as an example from an Apple TV, or you can see it on the sticker, usually on the label. There's a Ethernet ID, and it's a hexadecimal number. And it's a wireless. It has a wireless interface. It's a different interface. It has a hexadecimal number that is also different from the wired one. And you can see in this case that the first 3 are different. They're not the same, but they both belong to Apple. And this is a MAC address. Also, if you go to your laptop or you go to your desktop or even your phone, if you're on Wi-Fi, you can go to the settings on your network settings, and you can see that there's an Ethernet ID, or sometimes in Windows they call it out as a MAC address, and you can see the hexadecimal number that is unique to your device. So this is, MAC address is a layer 2 kind of address, and that uniquely defines that device. And you can think about it when you talk about the mail system. This is basically your address that the mail system will ship it to you. So the mail will most likely be assigned to a physical address, whether it's a house or an apartment or a PO box. But the intent that hopefully when you move, that address does not move with you. It sticks with the physical location. Now we go up, which is layer 3. This is when we get to more kind of a logical way, not a physical way of thinking about things. And the most common layer 3 protocol you will run into is IP, which is Internet Protocol. So the IP address, we can spend hours on IP addressing and why they exist and the way they exist. So that's a big thread that you can pull on yourself, or hopefully we can cover in next webinars. But you can think about it as the IP address is a way to define devices on the internet. So when the network was designed to scale, it was not designed to go only into what we call local areas, not designed to go only in a house or an office space. In the internet era, the network was designed from the get-go to be global. So there needed to be a way to logically assign IP addresses or addresses to identify devices or networks. Because if you think about it, if the IP address doesn't exist, and you have to really know the MAC address of your destination, then every device in the world would need to know the MAC address of almost every device in the world. And that is a lot of devices, and that's a lot of overhead, and that slows things down significantly. So by separating the physical address from the logical address, now we can do some innovation around the logical address and how we address things from a logical perspective. And can we group certain things in a network? And can we group certain geographies in a network? Can we group certain ISPs in a network in a way that it simplifies this communication across geographies and across the globe? But long story short, the IP address is a decimal addressing scheme. It's 32 bits. The one thing you need to know that usually the IP address is tied to what we call the subnet mask. And the subnet mask purpose is to logically define what is the network portion of the IP address and what is the host portion of the IP address. It means that, as the subnet mask moves, it's kind of a roller. If it moves more towards the host side, it means that, there are less number of devices in that network that communicate with each other. And as it moves up, it means there are way more devices that can communicate with each other on that network. Typically, in a residential environment, you see it scaling more to the right because if you think about 8 bits being in a decimal point, that gives us a total of usually about 250 devices, which is more than enough for a network for a residential network. But as you go to the other extreme, which is your internet service provider, those ISPs, especially the large ones, they serve big geographies, so they serve millions of devices or millions of networks. That subnet mask will tip towards the other end. The other thing that you need to know that IP addresses also are split into 2 buckets. There are private IP addresses and public IP addresses. So the way you think about it, the private IP address is something that the internet will not see, doesn't care about. If it sees that address, it will drop it. The public IP address is the one that is unique or should be unique across the globe. So it's a way to identify networks across the internet. So the other way to think about it, if there's a corporate office, and let's say there's our building here, Snap, we have a three-story building with hundreds of employees, hundreds of devices. All the IP addressing inside that building is private because all the messaging and all the mailing that we want to have inside the company is private between devices, and we don't want that to go across the internet, and we don't want that to go to be accessed from the internet. But from the ISP perspective or from the internet perspective, we have probably 2 IP addresses or 3 IP addresses that are public. So from an ISP perspective, this entire building, which serves hundreds of employees, is seen as only 2 or 3 IP addresses. So it's a different way of thinking about IP addressing. And that's the power of this addressing schema. So here's where you see it also on your computer. So we talked about if you go to your network card information, you'll see something called IP address. And almost always you see something below it called subnet mask. And the combination of 2 will let you know as a network engineer or as a network professional how many IP addresses are available for me in this network and whatnot. Then the layer up is going to be the transport layer, and this is a layer that bonds applications or content into the IP address. So that facilitates communication on an application level. So let's assume your laptop or your phone. It has 1 MAC address. It has 1 IP address, so you can access it physically on a MAC level. You can access it logically on an IP level. But inside the computer, there are multiple applications running. Now I have a browser that is open with multiple tabs. I have Outlook reaching out for email. I might have Pandora running with some music. So those applications, they have different types of traffic. They have different types of requirements. They open up sessions differently from one device, from one physical device with 1 physical address and 1 logical address. So that we needed a way to communicate on an application level. So this way, if I have, my Outlook open, that application is communicating with the mail server of Outlook of our company somewhere. So we need to make that one-on-one connection. So that's why we have the layer 4. Layer 4 has protocols and technologies that map applications to a device or a session. And the most common one will be TCP and UDP. So TCP, think about it as a way that it requires a handshake before that session is open. So basically, if I want to talk to Ricky, I will say, "Hey, Ricky," and he say, "Hey," back. I will say, "Do you want to talk?" And he'll say, "Yes," and we start talking. UDP is a way that doesn't incorporate handshake. So basically, the application just sends data to the server. Whether it receives it or not is somebody else's problem. And you can see, similar to IP addresses, there are kind of well-known port numbers and kind of a private port numbers. And you can see multiple applications that are well-defined and they've been around for multiple years. They have publicly known port numbers that are known to all networking professionals or all technologists. I would say the most famous is port number 80, which is HTTP traffic. So whenever you open up a browser and you type in google.com or facebook.com or whatever, it utilizes port number 80 to initiate that web traffic and communicates with a server on Google data center, for example, on that port that says, all right, I'm going to access the content on HTTP protocol using this port. So I'm issuing a web session. And the other way you can see it in the field is really around, when you have colon, when you type into your browser. So whenever you type in an IP address, and we've all done this, and you say, all right, we need to have colon and some sort of a number, that number is a specific TCP or UDP port number that is not publicly known and is not port 80. So if you don't type the colon specific port number, the browser automatically assumes this is an HTTP request and automatically assumes it's port 80. But in case where you see it, for example, in surveillance in MVRs and DVRs, sometimes you have to access that on a specific port that is not a standard HTTP port. So this is the way you can see it in real life. So this is, kind of to recap, this is kind of, an eye chart, but think about it, going back to the mailing system. Whenever you access a web page, whenever you access a audio stream, whenever you access a video stream or a Skype session or what have you, you are constantly sending traffic or sending content or sending payload from those applications that the user is interacting with to either a server or another application somewhere that interacts with it. And all the time it happens, thousands of times a minute, that message or that data that needs to be communicating with the counterpart data is being chopped off into multiple messages, and those messages, they move down these layers in order to communicate between a host and a receiver. So think about computer and a server, computer and computer, a mobile and a server. And you can see, the application's data becomes a payload to another layer that adds a header, and another layer that adds a header, another layer that adds a header, and then at the end of the day, layer 1 converts this message into bits that goes into electrical signal that goes ones and zeros across the network. And it's important to look into this picture and understand it, because if my traffic here is, let's say it's 1 byte or 1 megabyte of traffic that I want to send, I'm adding a lot of headers in order for that to get to my destination. And those headers, what we call is overhead. So let's assume that my pipe here capacity is 1 gigabit per second. I'm not utilizing full 1 gigabit per second to send actual data. I'm utilizing probably 60% of that pipe to send actual data. The rest of it is going to be a lot of communication, a lot of protocols, and a lot of technology that is designed to make sure that my traffic is getting from where I want to wherever I want. So other items or other jargon that you run into in real life is what we call DHCP, or Dynamic Host Configuration Protocol. So we talked about IPs being a logical address that is required in the network, and it's kind of a unique identifier for devices on a logical way, and that's very important. It's not burnt into the chipset. So sometimes those IPs, when we talk, especially when we talk about a private environment like the residential environment or an office environment, we decide to make it a private IP scheme that we want to give each device a unique IP address. So prior to DHCP, there will be network admins or system admins. They will go physically to each device or each computer and type in the IP address of that device one by one in order to make sure that they don't conflict, they don't overlap. So make sure that each device is getting one IP address, because if two devices get the same IP address, you can see there's a confusion. The same, a mail message is going to be sent to a recipient. If I have two Rickies in the same address, which one I'm going to deliver this message to? So that's not good. So the way people start to think about how to do things smarter rather than going one by one and typing IP addresses, they thought about can we do things in a more automatic way? And this is where DHCP come in. It's a protocol design, so it's a layer 3 protocol designed to automatically assign the IP address to a device. So let's say there's a DHCP server, so that server holds a pool of IP addresses that are private, and that server is responsible of assigning those IP addresses to different devices on the network and making sure that those addresses are unique to each of those devices. So this way, the system admin is only responsible of maintaining this DHCP server, one device. And whenever there's a client that is in DHCP mode, it powers up, the network interface goes up, the MAC address is burnt on the chipset, it needs to get an IP address. So it starts a kind of a four-way handshake process. The first process is what we call a DHCP discovery message, and that's a broadcast message. So we talked about the types of traffic being unicast, multicast, and broadcast. This is a broadcast message. The device basically says, hey, I don't have an address. Is there a DHCP server out there in this network? Then this DHCP server receives this message and raises its hand and say, yes, I am a DHCP server. Here is my IP address. So the DHCP server being on the network, it has its own unique IP address, and also it has its own MAC address. So it sends a reply to it, say, hey, I'm here. This is my IP address. Then the client says, all right, I'm going to send a unicast traffic. Now I know where I should send my traffic to. I don't have to send a broadcast to everyone telling them I know where I'm going. I know the respondent address. I'll send a one-to-one message, a unicast message, and say, hey, I need an IP address. Then the DHCP server will respond with the DHCP acknowledgement, say, yes, here's your IP address. I have you registered in my database at this address. And on the DHCP side, it basically maps the MAC address, the physical address of this network interface on the client side with the IP address that the DHCP server has given. So that's in a nutshell how DHCP servers work, and that's why they're important in your typical life, because instead of you going typing IP addresses to each device on the network, you can now go and make it very dynamic from a DHCP perspective. Now, we mentioned that the DHCP server has now a database of IP and MAC address, and another cool thing that you can do is make sure that this device is always getting this IP address, because that acknowledgement or that message going back to the client, it has a timeline to say, hey, this is your IP address for the next 12 hours. And after 12 hours, if this device doesn't check in again and say, I need to renew my IP address, then the DHCP server would assume this device is no longer in the network, and it frees up this IP address that it's given to it before to give it to someone else, because there are a finite number of IP addresses. So by a technology called DHCP reservation, which we will run into in the field, you can go to the DHCP server setting and say, this physical MAC address of this client is always associated with this logical IP address. And this way, it doesn't matter if this device goes offline or online or drops off. Every time it comes on the network, it gets the same IP address. This is important when you have, for example, MVRs on the network that you want to access remotely. You don't want those to have different IP addresses every time they go power on or power off. Another industry jargon that you will run into is DNS, which is domain name server. So we talked about the network being designed to go at scale across the world. So the IP addresses, while they're really good in terms of design of what they are intended to do, it's really hard for the end user to remember an IP address of a certain website they want to access. So imagine if instead of typing www.google.com, you have to type in an IP address. Let's say it's 8.8.8.8. Then you have to maintain a list of all those IP addresses of all different companies or different websites or different services you're trying to access across the internet. So that becomes really, really challenging. And that's where the network engineers and technologists, they designed a protocol called DNS. So DNS basically it's a combination of servers on the ISP side or in the internet, and their function is mainly translating a URL, which in this case is howstuffworks.com, to an IP address. So this way, for the end consumer, all they have to know is this URL. So they can type something that is more user-friendly, more user-readable, easy to communicate and translate. And when you type in, on your browser, howstuffworks.com, the laptop will initiate a signal to the DNS server and say, DNS server, hey, what is the IP address of this URL? If the DNS server has that IP address entry in this database, it will reply with it. If it's not, then the DNS server will ask other DNS servers in the internet. It's like, hey, I'm trying to reach you this URL to this website. What is the IP address? And somebody will reply with an IP address and say, hey, I know what it is. It's this IP address. Then it sends it to the DNS server. Now the DNS server will cache that address for future requests. If somebody else requested, it doesn't have to go through this process again, and will respond to the client with the IP address. And this way, as the message or this request moves down from the application layer, which is the URL in the browser, goes into a TCP session, which is port 80 on HTTP that we see here. It needs that IP address. Now it has that IP address, which is 70.42.251.42, and now it can go into that server and access that content. So that's another important technology term that you need to understand, and mainly it resides on the ISP. But sometimes if the DNS server of the ISP is down, guess what? Your client or your network traffic will not be able to reach either existing content or new content. And that becomes, for the end consumer a problem. They will say, hey, my ISP is down, but the link is up on the device. Or, hey, the network used to work and your network is not working anymore. When in fact it might be the DNS server on the ISP is down, and now all those clients or all those networks that this ISP is serving, they cannot reach those websites. So one of the tips that we use, we recommend dealers to use is put in some of the settings, put in a well-known DNS address. So basically, don't rely on the ISP DNS. Google has DNS servers for free, so our tech support can get the documentation for you. So hopefully, I know I went through a little bit fast. Hopefully, I covered a lot of the basic terms of terminology. Now we can go through some basic network design and build our first network. So from a network perspective in a residential space, there are really 4 building blocks or 4 components that you have to think about. The first one is the ISP component, which usually comes in a modem fashion. The second one is the gateway, which is the router. Third component is other network devices, kind of the infrastructure for your network. And the fourth item is the end devices. So this is your laptops, your smartphones, your tablets. So let's go know the modem. So the majority of the United States, it's cable mainly. Sometimes, in rural areas you find DSL. So this is an example of what you find from the ISP, or you can buy it on your own as a modem. This is a cable modem, and this is a DSL modem. So you can see this is actually the one that we recommend. It's an ARIS modem that we recommend not using the ISP modem if it's cable and buying your own. But if you're dealing with cable, which is the majority of the US, you will encounter something called a two-way splitter. And this is usually the ISP or the cable provider will install at the premise. And what it does, because the infrastructure of the cable, it carries both data, which is the internet, and video, which is the HD content that you can, or non-HD content that you can access as TV channels. And those two signals, they come into two different frequencies basically on that cable in order to minimize overlap, because the nature of that traffic is different and the requirements for those traffic is different, and you don't want your internet traffic to disrupt your video traffic and vice versa. So what they do is that from a frequency perspective, they separate the two signals significantly. This way you need this two-way splitter, which is basically a filter that filters one of those traffics and sends the other one the other way. So this way, think about it, it is data and TV coming in, it's data coming out and TV coming out. The next device that you run into right after your modem is the router or the gateway. That's the same, it's synonymous in the Resi world. And you see it in Best Buy or Amazon, you see a variety of shapes, forms, and functionalities. Some of them have Wi-Fi, some of them don't have Wi-Fi, some of them have dual WAN, some of them have multiple switch parts. But really, the function of the router is to isolate and communicate your internal network from the internet. So it becomes kind of the gatekeeper or the gateway to all the traffic that is going outside to the internet. And it's done through something that is called network address translation. So we talked about IP addresses being on the internal network as private address, and if there's a private address that goes into the internet, then the internet will drop that request, will ignore it. This way, the router will translate all the traffic, all the requests going from different devices in the network into traffic coming from one public IP address, which is the WAN, this is Wide Area Network Interface. So the Wide Area Network Interface is the interface that connects to the internet, and it has a public IP address that is unique to that interface from an ISP perspective. And the LAN, which is the local area network, is just the internal interface, the physical interface that interact with the internal network and translates everything through what we call NAT, network address translation. The next component down is the switch. So the switch, as you can see, there's a modem, there's a router, usually has some security in it or firewall functionality. The switch is what makes the network. The switch is the kind of the backbone infrastructure for the entire network. So think about the switch as a device that has multiple physical Ethernet interfaces, physical RJ45 interfaces, and it connects all those cables together that allows those devices to communicate with each other and communicate with the router or through the router to the internet. So this is what the switch does. That's why you have multiple varieties, multiple port counts. So if you have a 5-port switch, you can connect up to 5 devices. And if you have a 48-port switch, you can connect up to 48 devices on the same switch. So a switch also is not a singular device. You can connect a switch to another switch, and that switch also to another switch, and now you expanded your network in terms of capacity. So let's say if I have a 24-port switch here, I can connect up to 24 devices. What if I need to connect 30 devices? Then I can connect another 8-port switch to that 24-port switch, and now I increased my capacity in terms of number of ports that I can connect. The switch, since we talk about switch and wires, it's very important to talk about a technology called Power over Ethernet, or PoE. You will run into that a lot. So basically, it was designed around IP cameras and access points. And the PoE basically it kind of injects power, static, not static. DC volt power to power devices that are low voltage required to power those devices over the same cable that goes to communicate data. So you can see in this case there's an IP camera. It needs a network cable to transfer all the data or all the footage from the camera back to the network. But since we already have a cable, through the technology of PoE, we can inject power that powers the camera itself, and this saves us power cords and power bricks at the camera side, and make the installation much easier because not all locations have a power outlet, and makes it even cleaner. And you can do it through two ways, basically achieving the same result. One way is you have a regular network switch that you get a PoE, connect to a PoE injector. Basically, that injector takes that data and takes that AC power and put them into one cable, goes into the device. Or your switch itself will have multiple PoE injectors on the inside of it, or PoE functionality inside of it, and now it's a much cleaner install because you're already connecting that camera to the switch. So that's a PoE injector. You can see there's data in and data power out. The other component is wireless access point. And think about it, wireless access point is a way to enable Wi-Fi to work. So it converts a wireless signal to a wired signal. So it converts your airwave into bits and bytes going over a CAT cable. We're not going to dive into Wi-Fi a lot because we have multiple other webinars that covered a lot of Wi-Fi, but think of Wi-Fi, there are two main roads or highways that you can get onto. It's 2.4 gigahertz spectrum and 5 gigahertz spectrum. The 2.4 gigahertz is kind of an old highway. It's small, it's narrow, it's old, but it goes far. So it doesn't have a lot of capacity, it doesn't have a lot of speed, but it goes far. The 5 gigahertz radio is the new highway, which has more lanes. It has more capacity. Usually you're allowed to go faster on the new highway, but it doesn't go as far. So 2.4 has a lot of coverage, but lower speed. 5 gig has lower coverage, but a lot of speed. So that's it, in terms of components. These are the main components that you will run into in a typical network environment. You have the switch, which is the backbone of the network, which provides the function or the connectivity between multiple devices over wire. You have the router or the gateway, which is the gateway to the internet. It does a translation between the local network and the internet back and forth. And you have your wireless access point, which basically enables Wi-Fi signals and converts your wireless signal to a wired signal. So let's go and build a very, very simple network, a basic network that can connect multiple devices, have a couple of laptops, a couple of smartphones, a couple of tablets, wirelessly, and we have some wired devices like a desktop or a printer, a Sonos Connect and an Xbox. So it's a very, very small network that we want to make it, you want to create that network. So like we said, we start with the internet service provider. So we get the modem from the ISP, or preferably if it's cable, you switch that ISP cable modem with something that you trust and is reliable. Then you connect it to the router. Then from the router to the switch, and from the switch to a wireless access point to enable these Wi-Fi devices to talk. And this is actual footage of one of our customers, and I like this message, footage or this picture they sent us because it kind of deconstructs the network a lot in an easy to follow way. So you can see here, I'm not sure if you're following my pointer, you can see this black cable. That's the cable that's coming from the cable provider. That's coming from the ISP. And this box is the ISP cable modem. So this is the cable modem that converts the cable signal into an Ethernet or RJ45 signal. So this white cable coming out of the modem is an RJ45 that goes into our router and goes into the WAN interface of the router. And then the blue cable is on the LAN side, or the local area network side of the router. So that's the inside of the network. It goes as a blue cable into a network switch. And this is actually a PoE switch because it connects to a control port, it connects to a WAP box, but also there's this white cable going from the basement up. It's most likely going into an access point that provides Wi-Fi connectivity. So this is a really basic network. Now this, you can see it from a logical or topology perspective. It's very, very linear, very easy to use, and you connect multiple devices to it. And this is how you see it in real life. There's a cable to a modem, modem to WAN interface of the router, LAN interface of the router to a switch, from the switch to all devices. That includes a wireless access point. Very simple. So that's it. Before we, go into Q&A, there are, where you take it from here from a knowledge perspective, this is really basic. Any slide that I have in the webinar, you can spend hours digging into that thread and understand history, technologies, challenges, and multiple innovations that happened over years. YouTube really has a lot of content from networking perspective. You just go open up YouTube and say, hey, networking 101 classes, and you can find somebody's doing some basic course that explains networking, but usually from an IT perspective. But the space itself has been 25 plus years old. A lot of innovation, a lot of history. Everything. The good thing is about networking is almost everything is standardized through IEEE. So there's a lot of standardization, a lot of shared knowledge. There's not a whole lot of discrepancy across the board. There are a couple of really entry-level courses that if you want to take something that's more standardized fashion. There's CompTIA Network Plus. From Cisco, there's CCENT, which is the certified entry-level technician. These are more IT focused, I would say, than AV focused, but they provide a good foundation in terms of knowledge that you can run into. So if you want something more formalized that gets a certification at the end, these are really good starting points. There are a lot of industry resources out there. Whether it's snapav.com, whether CE Pro or some webinars that we've done, there are a lot of resources that you can tap into that gets you to various topics, but it's not put together in a way that takes you from start to finish. It's something that we're working on probably. Hands-on experience is very, very important. That's what I found when I started on my journey of networking. It was very, it's the theory part of things and topologies and whatnot is very nice. Kind of like this diagram, but once you write something on the paper or you see it in your head and you start to go to real life and it's like, all right, how do I put these things together? This is really good hands-on experience, but also you run into issues as you go and install your networks, and the tendency is to call tech support, which is the right way to do it. But as you go and fix a problem with tech support, make sure ask your tech support agent why those things happen this way, and they'll be more than happy to share some knowledge. And this way, you understand what's going on and why the things happen the way they happen, and that adds to your experience and adds to your portfolio of knowledge. We had, like I said at the beginning, we had a lot of webinars this year. This is a small list of things that we've done so far. If you want to take it to the next level, we had a webinar about network design, kind of expand this basic network to more complicated network. We talked about Sonos, VLANs, and we expanded a lot of switches and IGMP snooping. We talked about, from a Wi-Fi perspective, talked about fast roaming. We talked about truth about Wi-Fi speeds. We had a co-webinar with a company called MetaGeek that we partnered with that provide a lot of entry-level Wi-Fi technology explanation. If you want to have access to all these things, either go on YouTube or Vimeo, or you can send an email to webinars@snapav.com, and Ricky will be more than happy to share those links with you. And with that being said, Ricky, let's go through some Q&A. We have about maybe 5 minutes.
All right, just a few questions, and like always, loads of network information for guys who are just coming on board with networking. Let's take a couple of quick questions, and then I've got a question or two I want to get some clarification. This one looks like a little bit more about bandwidth. If you could speak to it for just a second or two. Why is networking still advancing the Cat 5, 6, 6A, 7, etc., and not moving towards fiber use?
Oh, it's a great question. I don't think it's not moving towards fiber use. The fiber technology in networking has existed for, I want to say, 15 years. It's really different between applications. So if you think about the networking space as a space, it's a multi-billion-dollar industry. All the innovation and or the majority of the innovation and R&D funding and investments happens on the top tier of the space, which is the internet service provider and the data centers. Just because the size of the businesses, the size of the markets are massively bigger than anything else. So those markets, they've had fiber connectivity for 10 to 15 years. I personally installed fiber networks as backbone for ISPs about 10 years ago. So that technology existed, and that technology existed for a reason, which is pushing the envelope on the speed. So all those speeds that you see on ISPs now, and all those services that you can do 4K streaming from Netflix perspective, had we not had those data center connectivities, they can go up to 100 and 400 gigabit per second per connection. We couldn't be able to serve those applications at that velocity. So I would say that the networking space itself have adopted and have innovated on fiber connectivity a lot, but the Resi space, that's a good point. The Resi space, it comes down to cost. I think the cost of fiber historically has been more expensive than copper. That has changed in the recent years because copper price point is, from a CAT perspective, is rising or fluctuating at the very best, and fiber with commoditization is going down. Then I think there's a hesitation from the dealer base, because fiber itself is very difficult to terminate. It's very expensive to terminate. The interfaces on end devices, they don't exist on laptops, for example, that have fiber connections. So there are a lot of costs that is outside of the actual cable that makes fiber less attractive in a mass market perspective. But good question. I think that the industry will move to it slowly. As I think it's going to be over the next 5 to 7 years, we'll get more fiber. But there has been also some innovation around the existing CAT infrastructure that gets speeds beyond 1 gigabit per second. I think up to 5 gigabit per second, which will be standardized this year.
Okay. All right. Just I usually get quite a few questions myself, Aham, and all we got is a minute or two left. But I really wanted you just to speak a little bit about the ISP's provided product. They're doing a lot of these all-in-one modem, router, switch combo boxes, and throwing these in every homeowner's home. And we as a company really discourage that and would like our dealers to turn off all those functions and use individual pieces. If you could talk about that situation, and then in conjunction with that, when I first got involved in networking, I always thought the router was kind of like the key component in there, but we're moving more and more toward the backbone of the whole network being a switch, and why it's so important to use a managed switch as that first router on a stick type configuration. If you could just talk about those 2 points real quick.
Yeah, great points. I think the ISP kind of the box, so to speak, you think about it. So think about it from an ISP perspective. The ISPs, they serve the masses, and from the masses to them is end consumers sitting in small apartments or small houses, and they want just connectivity. So they want something that they can plug into, get to the internet, and that's it. When we talk about our CEDIA market, those networks inside those big houses and big networks, they're way more elaborate. They're way more, let's say, dependent on the network. We have way more devices inside a CEDIA home, quote unquote, than the average home. So that makes the box that is provided by the ISP is not designed to serve that application. When you throw in a switch and a router and a Wi-Fi interface into one box, something's got to give, because either the box will be super expensive or something's got to give from a performance perspective. And those ISPs, since they hand out those cable boxes with a subscription for free, basically, they are encouraged to find the cheapest box possible that just does the job. It does the job in a perfect way. So that's why we encourage dealers to say either if it's a cable, there are way better alternatives as modems than what's provided by the ISP, fully knowing that something like Fios, you can't change their box because they tie HD to it or the TV service to it. But if you separate those components to, the modem being the modem, the gateway being the gateway, the switch being the switch, and the access point being the Wi-Fi, now you have specialized devices that are built for that kind of a function and application, and it can scale and can perform under pressure and under heavy load from the network that you can find typically in the CDM market. Your other point about managed switches versus unmanaged switches, I think we'll run out of time about that, but there's the webinar that I mentioned, which is Sonos VLANs and switches, talks about unmanaged switches versus managed switches, but in a high level, the first switch on the network being a managed switch, it gives you a lot of control over the traffic if that network expands to be bigger than the basic network that we saw. So the basic network that we constructed is really a simple network. An unmanaged switch will be just fine for that. But if you want to expand that network to serve more devices, more applications, different types of traffic that you can have, multicast traffic inside your network, broadcast traffic inside the network, a managed switch will help you eliminate a lot of the noise that can generate from those types of traffic and contain that into kind of virtualized way. So it expands the logical separation, so to speak, of devices to inside the network.
All righty, that's about all we have time. In fact, we've gone over a couple of minutes. I want to thank everyone for taking the time and viewing our webinar today. As Aham mentioned, we do have a few other webinars in our library that we'll be happy to share with you guys. Just send an email to webinars@snapav. It actually comes to me, and I'll send you back some links so you can take some of our previous webinars that go into much more detail and much more depth, obviously, into networking. We thought it was very important just to get kind of some basic information out for the guys who are just getting involved in networking. Again, look for a follow-up email from us in a couple of days. It's going to have a link to this recording. It takes us a little while to process this video and get it posted, but you will get a follow-up email with that link that you can share with your other employees if need be, or take a look at it again. Please take just a moment to fill out the brief survey as you exit the webinar. This lets us know your thoughts of today's presentation and what other topics you'd be interested in. And again, on behalf of Aham, Arachnus, SnapAV, and myself, I want to thank you very much for taking the time to join us today. Have a great day and happy installing. Thanks, guys.